Okay, so for your notes today, first, I'm sorry I'm not there, but I think you guys can do all of this. You're pretty smart, so I think it'll be okay. But this way I can still talk you through some of the slides. Forgive me in advance if I stumble through my words. It's difficult to talk to you guys when you're not here. I'm just sitting in my dining room talking to my computer. And so we'll get through this as best we can. We're going to do a quick review of KSP again, and then we're going to talk about what happens when I have what's called a common ion in the solution. So as a recap, if we're talking about KSP, we're talking about the solubility product constant. And what that means is there's a equilibrium that exists between the dissolved ions that are in solution and what's actually precipitating. So that equilibrium exists because even though you're putting in a solid salt in just water, in the beginning, some of those ions are actually dissolving. They're moving into the solution, and we're going to have way more ions going into the solution and dissolving in the water than that movement towards precipitation, because some of those ions are still going to come together and stick together and precipitate at the same time. There's an equilibrium between the two happening. Eventually, we get to this point that rate of dissolution is going to equal out to the same rate that things are coming and sticking together or precipitating. And when that happens and that equilibrium exists, you're not going to have any change in the concentration, because the number of ions that are separating and moving into the solution will be the same rate as the ions that are actually moving towards that solid form. So we can quantify those relationships between what's dissolved and what's still in the solid form with a KSP, or solubility expression. So if I have a reaction like this, generic salt AB dissolving into its ions, remember that you're going to write the KSP this way. This is the expression. So remember that you're using the coefficients as the exponents in the KSP, and remember that when you write your equation for dissolution, that you have to pay attention to that ratio of ions in the salt, and that ratio of ions is determined by the charges. So as example, if I have PbI2, I'm actually getting lead ions with a +2 charge, and I'm going to have 2 iodide ions for every lead ion that's dissolved. You'll see that in the actual formula for the salt, but you can also determine that because you know the charges on the two. So you know that we have to have 2 iodine ions for every lead ion, and so we're going to dissolve into 1 lead ion plus 2 iodide ions. You have to use that 2 in the KSP expression and square the iodine to get the answer for this. Remember that the greater the KSP is, the more soluble the salt will be in water. And that makes sense. If I have a high value for KSP, I'm going to get higher values for the concentrations of lead and iodine in the solution. So I've dissolved more with a higher KSP. There's some definitions that are important for you to remember. And most importantly, solubility, molar solubility, and KSP are different. Solubility is really the quantity of the substance that will dissolve to form a saturated solution. We often quantify this by talking about molar solubility, which is concentration. It's the number of moles of the solute that you can dissolve within a liter of solution. So this is going to be like a moles per liter concentration value. KSP is not a concentration. It's the solubility product based on the amount of ions that are dissolved in the solution. It's the product of multiplying the concentrations of the 2 ions to their coefficients. The KSP isn't going to change. This is going to be the same at every temperature for a certain salt. However, you might be able to dissolve more or less depending on what's actually in the solution. And that brings us to the common ion effect. So let's go back to that equation of lead iodide dissolving into lead and iodide ions. A common ion is a mixture of ionic substances that's common to the formulas of at least two. What that means is, let's say I were to put some sodium iodide in with some lead iodide. That sodium iodide is going to be really soluble. I'm going to have a lot of iodide ions present already. And so when that happens, based on the KSP, you're going to actually have much less of the lead iodide that could actually dissolve. The reason is our KSP stays the same, but now the value of the iodide ions in the solution is going to be really high, which means in order for the KSP to still remain the same, our lead ions that will be in the solution are going to be really low. So just a little bit of that lead iodide will actually dissolve now that I have some iodide ions already present in the solution. So the solubility of the lead iodide is going to be reduced if I put some sodium iodide in that solution as well. As I already said, the KSP doesn't change, but the amount of lead iodide that could be dissolved is less due to the iodide ions that are initially present from that sodium iodide that was put in the solution. Here's what it looks like. If you have lead iodide dissolved in water, I'm going to have a KSP of 7.9 times 10 to the negative 9. So the molar solubility is going to be found by using KSP. I'm going to take that 7.9 times 10 to the negative 9. It's going to be equal to the change in concentration, or the equilibrium values for lead iodide, I'm not saying this right, lead ions times the amount of iodide ions squared. You're going to get 4x3, or 4x to the third for your value for changes. And you'll get an x value of 1.3 times 10 to the negative 3. That's going to be the change in the concentration of the lead ions that will dissolve. You're going to end up with 1.3 times 10 to the negative 3 moles per liter in the solution. So you must have dissolved 1.3 times 10 to the negative 3 moles per liter of lead iodide. There's no common ion that's present here. But let's say we dissolve it in 0.1 molar sodium iodide. This was my original equation. And initially, now I have nothing. I don't have to worry about this concentration. I actually do have some here. Who cares? This amount doesn't matter because it's solid. You're going to, I'm sorry, I'm pointing and you can't see it. The lead iodide concentration doesn't matter because this isn't included in that expression. But I do know that I have no lead ions present right now, initially, when none dissolves. But I do have 0.1 moles per liter of iodide ions. The change is going to be, I'm going to say x for the lead ions, and I'm going to have to say 2x for the iodide ions because I get 2 for every 1 lead ion. When we look at the equilibrium, we know that the change in lead ions will equal x, and the concentration for iodide ions would be like this 0.1 moles per liter plus 2x. However, we had a really, really small KSP. That KSP is so small that this change or addition of other iodide ions is really negligible. We had a KSP value that was just 7.9 times 10 to the negative 9. So I don't have to do the plus 2x included in the 0.1 molar solution for the iodide. All I care about is the 0.1. This is going to make your math really easy. And if you plug your answers for x back into KSP, you'll see that the values work by just assuming that the 2x is negligible compared to the 0.1 molar that you already had. So when you plug that in, you'll just have x times 0.1 still squared. And you get that x is 7.9 times 10 to the negative 7. That's the actual concentration of lead ions that will be in your solution now, which means we only dissolved 7.9 times 10 to the negative 7 moles in every liter of the solution now that we had a common ion present because we had iodide from the sodium. So our molar concentration is 7.9 times 10 to the negative 7, or molar solubility is only 7.9 times 10 to the negative 7. Much, much less than we had originally. Another important thing to consider is that when you dissolve two salt solutions and there's a common ion present, that salt that has the lower KSP is always going to be the one to precipitate first. So as an example, let's say you have silver chloride. It has a low KSP, 1.6 times 10 to the negative 10. X squared, if I were to set this up, is 1.6 times 10 to the negative 10. And your X value, or the concentration of silver ions, is the same as the concentration of the chloride ions. That's going to be 1.3 times 10 to the negative 5th moles per liter. Some of that silver chloride will precipitate when the silver chloride is added because the molar solubility of that solution is much less than the silver chloride alone. If you have 1 milligram of sodium chromate added to 225 milliliters of a 0.00015 molar sodium nitrate, we can see if a precipitate's going to form. We're going to write the equation, silver chromate dissolving into silver and chromate ions, and we need to determine the initial concentration of the ions. The silver we can find is 1.5 times 10 to the negative 4. And we know that because it's coming from the silver nitrate, and we know that we've got a soluble salt here due to nitrate ions. If that's completely soluble, and I started with 1.5 times 10 to the negative 4 molar, I'm going to get 1.5 times 10 to the negative 4 molar silver ions. The chromate ions we can figure out based on the milligrams of sodium chromate and the volume. We know this is also soluble because alkali metals, salts with alkali metals are soluble. So I can say that this whole thing's going to dissolve too. Take that mass, divide by the molar mass, get the number of moles, which is 6.17 times 10 to the minus 6. You're going to divide that by 0.225 liters because we have to convert the milliliters to liters. And we get that concentration is 2.74 times 10 to the negative 5. So we're going to compare that initial concentration to the solubility product constant. That initial concentration of ions, or silver ions, squared times the chromate ions, that should all be on the same line, is going to equal, when we do the math for that, this is like a Q value, 6.2 times 10 to the minus 13. The KSP for the silver chromate was 1.1 times 10 to the minus 12. So since this number, the 6.2 times 10 to the minus 13, is so much smaller than the KSP for the silver chromate, we can determine that we're not going to get a precipitation reaction. There won't be any precipitate that forms. However, if we knew those concentrations and they were different values and we could plug it in and we saw that we end up with a concentration that's way higher than KSP, we could determine that we are going to have a precipitation happening in this solution. So let's go through your steps. Just to recap, step 1, if you want to predict if that precipitation is going to occur, write the balanced equilibrium or the reaction. So silver chromate dissolving into silver and chromate ions. Then write the KSP. Figure out what that expression is going to look like, and you'll get the value based on the solubility product constant tables that will be provided, or the numbers going to be provided to you in a question. These are standard values based on the temperature and based on the salt that will be known values. Step 3, determine the initial concentration of the ions. Once you figure out what those are based on the information that's giving to you in the scenario, plug them in, see what happens. Calculate your KSP or your Q value. This is 7.8 times 10 to the minus 13 is essentially a Q, or the ratio of the products based on the concentrations that you have. And then you're going to compare that value to the value for KSP. We see that this one is much lower than the KSP. So we figure that no precipitation is going to happen. I hope that clears things up and makes it easier for you to work together on the common ion effect on solubility worksheet. When you do this worksheet, it's really important that you pay attention to the directions. So you're going to have to read, you'll see a note at the top under Model 1. It says, proceed to question 1. Do not fill in these tables until instructed to do so. That's really important. You're going to work through questions 1 through 7 before you actually dive into number 8, which is filling in the table. When you fill in the table, you guys might want to split up these values, but once you determine what X is and what the concentrations at equilibrium will be, plug them back into the KSP equation to see if your X values actually work out to be 5.5 times 10 to the negative 6 for KSP. You'll know what I'm talking about if you're looking at it right now. Look at it right now. Okay. One thing that you're going to want to remember to do is that if you have a significant concentration of a common ion present, which you'll find in, for instance, beaker 2, that change in that common ion at equilibrium is going to be so small that you don't have to consider the change. So, for instance, beaker 2, how you have 0.2 molar initially. When you add in that change, which will end up being like 2x, you don't have to factor the 2x into the equilibrium expression, or KSP. It's going to make your math super simple. In other words, the hardest math that you will find in these equilibrium expressions and solving for the concentrations, the hardest one is actually just beaker 1. That being said, I think you can finish the whole thing. I'd like you guys to give it your best shot. And then don't worry about doing it for homework, but work really hard as a group to finish it so that we can come in and talk about it when I'm here on Tuesday. Yeah, that's it. Your test is going to be next Monday instead. I updated Canvas, and hopefully that is helpful for you. Okay, I'll see you guys tomorrow. Thanks. Bye.